All right, so we'll start with our session. So in today's session, we're going to see about static characteristics of sensors, right? So in the previous sessions, we saw what sensors were, and we saw what are transducers. Then we saw different types of sensors. Then we saw different types of transducers. And in addition to that, we also saw how camera sensor works. And then we also saw how fingerprint sensor works, the measurement system behind it, the instrumentation system behind it, right? So we saw all those. So in today's session, we are going to see about static characteristics of sensors, right? So uh, if you remember in the first session I told like what we are going to see in that category. I mean, like in that session I told that we will be learning about static characteristics as well as dynamic characteristics, and you all said that difference between you all knew the difference between a static and a dynamic characteristics. Here we are going to study about the static characteristics, which means what are the characteristics expected when it is not in motion, when it is in rest, right? So these are all the characteristics that we will be learning, or we are expected to learn. The reason is only if we know this, we can rate whether the sensor is good or bad, whether the sensor that we have taken is good for our project or not, right? So these are all quite common terms, so you don't have to worry about it. Most of us know what accuracy is. Then we know reproducibility, general word. Then drift, repeatability, noise, accuracy, precision, sensitivity, linearity, hysteresis, threshold, right? Dead time and dead zone, resolution, right? So all this, like it's a common English word, and you already know what they are, right? So now we are going to see this in the perspective of a sensor, right? So before getting into that, we need to know some basic terminologies like this. First one is true value, then followed by best measured value. Okay, there's a typo, it's not BESI, it's best measured value, then static error and correction, then range and span. So these are all normal words that you should know before getting into measurements, right? Basically we are going to measure using sensor, right? So to study about the characteristics of sensor, we will be needing this terminologies which are used in measurement, right? So the first one is true value. True value is the ideal value, right? uh, uh, you all know the ideal value of gravity, right? You all know what is the room temperature. There's something called as gas constant, temperature constant, right? So this constants means these are the ideal values, right? Hope you know the ideal value, right? What is gravity's ideal value? Gravity value, anyone knows what is the value of gravity? 9.8. Okay, good, very good, very good. 9.8 is the ideal value. Room temperature, any idea about room temperature, body temperature? Okay, so if you haven't studied that earlier, room temperature is supposed to be 27, and your body temperature is 37, but warmer than the room temperature. Okay, so let it be aside. So true value is the ideal value. Next, best measured value is the value that we measure, and that value, if it is closest to the ideal value, then we can call that as a best measured value. Like for example, in your 12th standard, while measuring the center of gravity, again same center of gravity, while measuring it, you'll be playing with pendulums, and you will be measuring the time to and forth, and you will be getting some kind of answer, right? So most of us would got answer somewhere around 9.6, 9.7, right? So the value is not ideal, but it is close to the ideal value, right? So if you have got 9.6, 9.7, then 9.7 is the best measured value for center of gravity. And even in your basic electronics lab, if you have done this diodes experiment, you will measure the barrier potential. The barrier potential of a silicon should be somewhere around 0.7. But if you while doing it, you may not get exactly 0.7. You'll be getting somewhere around 0.65, 67, 0.7172. So the one that is closest is considered to be the best measured value. The next one is static error. Static error is simply the difference between true value and measured value, right? So we are going to call it's a general difference. We are going to give it a name as error. Since we are dealing with static characteristics, we are going to give it as a name as static error. Okay, so static error is the true value minus subtract, measured value. Okay, while doing the calculation, if suppose the measured value is larger than true value, then you have to do the subtract in the other form, like measured value minus true value. It cannot be the minus form in most of the cases, right? So next one is correction. Correction is the inverse of error, right? So it's pretty much reliable on an error is the inverse of correction, right? The next one is range and span. Okay, here I want you to listen, because these two terms may confuse you. Okay, range and span. Range is the measure between maximum and minimum value, whereas span is the range between maximum minimum value. Okay, so this could be confusing. So to help with that, look at this experiment. This example. Let's say there is a thermometer which can measure between minus 40 degrees Celsius to 100 degrees Celsius. So in that case, the range is minus 40 to 100, whereas the span is the 40 plus 100, which is 140. Right? Hope you can understand now. The difference between the range and span is that if it's in as per this experiment, example, there's a thermometer, and this thermometer can measure between minus 40 and 100. So for that particular thermometer, while writing the specifications, you can write the range of the range of that particular thermometer is from minus 40 degrees to 100 degrees, as the span is 140, which is the sum of minus 40 and 100. Okay. All right, so these are all the basic terminologies you should keep in your mind: true value, best measured value, static error, correction, range, and span. Okay, the next is accuracy. Okay, so accuracy, as I told, it is the measured value which is closest to the ideal value. Right, we will always look for a system or a device which is very accurate, right? Because that is what we want. We don't we can afford to have so many loss, so many errors. Right? We will always go for a machine or a system that is pretty accurate. Right? Only that will give you better result. So for determining that, we use this particular term called as accuracy, which is the measured value that is closest to the ideal value. Right? So in case of gravity, the ideal value is 9.8 meter per second square, right? But
Right. So it is the measured value which is closest to the ideal value, right? So you while doing experiment, you will be getting value that is closer to 9.8, right? So that means your value is accurate. So now look at this slide. Here the red color dots denote ideal value, whereas the blue ones denote measured value. From the first one, you can see we have got only the ideal value. In the second round, you can see that the measured value is pretty much closer to the ideal one, so we can call that a system with good accuracy. Whereas in the third diagram, the blue dot is somewhere far from the red, so that is a system with poor accuracy. And now
as I told, you'll have to be very careful in understanding the difference between a system with good accuracy and a system with good precision. That is the difference between these two terms, accuracy and precision. Right. Next is precision. This is very important. You can understand better from the diagrams. The statement is it is the degree of agreement with a group of measurement. Right. So I like to tell you this thing: while doing experiments in your laboratory, you will not stop with single iteration, whatever the experiment may be, whether it is finding the barrier potential of a Zener diode, or while doing proving Thevenin's voltage law, or while proving Kirchhoff's law, or whatever the experiment may be, irrespective of the nature of the subject. Whatever the experiment you do, to get a correct value, we will do more than one time. Right. So while doing that more than one time, if the values are near to each other, like if it is only plus or minus 0.5 or zero 0.6, then the system is said to have high precision. Whereas if you, while measuring first time, if you get 5, in the next time if you get 20, in the next time if you get 40, in the next time if you get minus 20, then the system will not be precise. Right. So that is the concept, or just the understanding. right? So precision is like the degree of agreement with a group of measurement. Let's take the same experiment as a center of gravity experiment. While measuring the center of gravity experiment, while playing with your pendulums, you would have taken more than one values. Or in your chemistry lab, while doing titrations, you will be taking more than one iteration, right? So at the end, you will put the average value, right? In human anatomy lab, you will also do the same thing while measuring your blood pressure and pulses. You will be doing the same thing. You will not start with just one value. You will take 3 to 4 values and then take the average, right? So when while taking the 3 or 4 values, that 4 or 3 values should be like close to each other, right? If it is far from each other, then we may have, then that system is not precise, right? So this is about accuracy. Accuracy is like the difference between, or the value that is closest to the ideal value, whereas precision is group of values that should be close to each other, right? So I hope you understood the difference between accuracy and precision, right? Accuracy is closest to the ideal value. Precision is a number of iterations which are closest to each other, right? It doesn't have to be closest to the ideal value, but it is closest to its own group of a group or a number of experiments being done, right? The next one is repeatability. Okay, so here while starting with it, with this, I would like to say another thing. While studying or while trying to understand this term, I want you to compare and understand this term with the next term. See, this is repeatability, whereas this is reproducibility. Okay, so these two terms may confuse, but to help you understand better, I've given the diagrams in the background. First is repeatability. Repeatability means repeating an experiment many times by same person under same condition. You can like understand from the diagram, in the first try, women is trying some experiment and she is using a AC, like she is maintaining a temperature. The outside there is a sunlight, and the same woman is trying like 74th time the same temperature with the same temperature outside, so every condition is same, right? So that is repeating the same experiment. Reproducibility on the other hand is repeating the experiment many times by different persons under various conditions. Okay, so in this case, you can see from the diagram, first women is trying an experiment, whereas in the 74th, a completely different person with a completely different AC, completely different setup, completely different environment is doing the experiment, right? So repeatability, reproducibility. Repeatability is repeating the experiment by same person under same condition, whereas reproducibility is by same person under various conditions. Okay, so repeatability is used mostly when you're like developing a new vaccine, right? Reproducibility is by testing it, right? So this both are important to determine whether your sensor is good in reproducing or repeating the values, right? The next one is noise. So I don't think I'll have to give any big uh, explanation about noise. It's quite simple. You can understand from the statement given here. Noise is a meaningless or unwanted signal. The best example would be your television set, right? When there is no cable connection, when you turn on the TV, you'll see that grains, right? So there are noise, noise in the TV or in the video, right? Whereas if you have a good proper good cable connection, you can see the picture. That is the signal, right? So that's it. It's pretty simple, right? So here, to determine about the noise or to understand the characteristics or like the noise in the system, we use a term called as signal to noise ratio. That SNR stands for signal to noise ratio, right? You can understand from that formula. SNR is equal to signal for, by noise. So how much signal can be obtained in spite of noise, right? So that will give you the presence of noise in a given signal. Okay, so from based on this formula, can you tell me like should we have high SNR or low SNR for a good system? If you think we need a high SNR for a good system, put number 1 in your chat box. If you think we need low SNR for a good system, put number 2 in the chat box. What do you think? look at the formula. It says signal by noise. So what should be SNR? Should it be high or low? You got response only from most of you are not responding. Am I being am I clear? Okay, now I'm getting responses. Okay, thank you. Right. So the answer is number one. We should have high SNR. See, we are dividing a signal by noise, right? So our intention is we should have low noise, right? So only if the value at the bottom is low, I mean, if that is the ideal thing, right? Noise should be low. That means the system is good. So noise low means the value of the noise should also be low. So if something in the bottom is low, then SNR will be high, right? So to an ideal system or to a good system or a perfect system, SNR should be high, right? So the answer is 1, right? So the reciprocal of SNR is noise factor. Most of the terms, I mean, in your electronic subjects, you will be coming across this. It will be, I mean, it is to be denoted by F, which is the inverse of SNR. Okay, SNR is signal to noise ratio. It should be high for a good system, right? So noise is a meaningless or unwanted signal. We don't need that signal, or most of the time we will only try to overcome this noise. We use so many filters. I don't know if you have studied about filters and all. We will be using filters and so many things. Even in your mobile phones, you'll be using the beautification apps, right? Like B612, Rhetoric, and all those apps. What they do is actually they filter the noises. Right? Only with that kind of effect, you can like see a very good image. Even a bad image can be transformed into a very good image. Right? The reason behind that is software filtering. Okay, it will filter out the noises. Right? Okay, so that's it. Noise. The next is different sources of noise. Like if you see there are different sources of noise, like generator noise, conductor noise, radiator noise, right? So how to differentiate them is, if you take a generator noise while performing a certain operation, there will be some noise that be coming along with the normal output. For example, the best and ideal example would be, we have fans, right? In our home we have fan. When we switch on the fan, the output of fan should be airflow. But in addition to the airflow, there are some kind of errors or noise that will be coming outside. Right? You can hear your fans sound, right? So that is noise that is coming out, noise that is being generated along with the normal output. Right? So that is one source. The second one is conductor. Conducted sources, like if you see in transformers, you can hear small humming sound, right? While energy is being transferred from one place to another, the transformer, you can hear small humming sound, right? So that is conductor noise. Then radiator noises, like what you see in speakers. In speakers, if you see, at times there will be some kind of squeaky sounds, then there will be some blur sounds because of the paper in the speaker. So those are all radiated noise, right? So be clear with the noise sources. I think the images in the slide can help you understand. First one is generated noise. It mostly occurs in machines. Even in your motorbikes, if you see, while you start the engine, the purpose of the engine is to put the wheels under rotation. But along with that, we hear some sound that is not actually sound. Those are noises, some kind of errors. Right. Then second one is conductor. You can understand from the transmission line, the conductor noise or the sound that we hear in the transformers, small humming sound. Then radiator is a sound that is radiated outside in some repaired or not proper speakers, right? So these are all the most common sources of noise. And then we move to the next slide, which is drift. Okay, so drift is very simply said, it is lagging in time. You're supposed to be at, okay, class by 10:15, right? Into, as per today's class, you should be here by 10:15, but If you come by 20, then I can say it as a drift, a lag in time, a lagging by 5 minutes, right? So that is the best example of drift, right? So drift is simply put, it's lagging in time. So under that, we have some types, let's say zero drift, zone drift, and combined drift. Okay, I hope this pictures can explain it. In zero drift, if you see, the black color arrow mark is the ideal one, right? Whereas the red one is the drift. In the first picture, I hope you all can see the picture. Yes, okay. In the first picture, the zero line itself is drifter. The zero obviously should be this point, right? This should be the zeroth point, the origin, 0 comma 0, as you study in your graphs, 0 comma, that should be the 0, that should be the starting point. But due to some issues, the value starts somewhere else, right? So like if you take our class, it should have started here 10:15, but if you come like 10:15, this is how your graph will go, right? So that is a zero effect. The next one is zone effect. Zone drift, it happens in a particular zone. So initially it was correct, initially the value is correct. When once you progress along a particular zone, it will start deviating. That is called as zone drift. And the third one is combined, which means combination of both zero and zone, right? Okay, so this is drift. I hope you can understand drift also. So we'll move to the next one, which is sensitivity. Sensitivity is like the response of the system to the minimum value of input signal. Let's take a system, whatever the system may be. If you take a system, and if the system gives output, I mean, obviously system will give output if you give them a input, right? So sensitivity is the minimum input that we give so that we get an output, right? So we say sensitivity in most of the cases, right? In a system, in motors we say sensitivity, in a system we say sensitivity. I would like to give you a good example, the touchscreen sensitivity, right? uh, I hope you know this two types of touchscreen. One is resistive touchscreen, capacitive touchscreen. I hope you would come across this. uh, right now we don't have any mobile phones with resistive touch, but when touchscreen mobile phones were introduced, most of the mobile phones were having only resistive touchscreens. Okay, so resistive touch is like, you you don't need just a, I mean, apart, like not only the fingers can be used, I mean the fingers should be used, we can use more than that. Like we can use a normal pen, you can use your pencil to touch the display, resistive touch. Whereas in capacitive touch, it's completely different. Only with your finger or specialized device you can operate the touch screen. Okay, so to help you understand, I think this small animation will help you understand. So if you see this, the first part is the resistive, the second part is capacitive. So in the first part, what happens is when you touch, the screen will bend a little. So based on the bending, the resistance value will change, and as per that, the electricity will be captured, I mean the signal will be captured, and the system will process which region is being touched, right? But the problem here is you can do only single touch in resistive screen. Okay, also in resistive display, you'll have a you'll have to obviously keep a flexible or a bendable screen. So if you keep a bendable screen, what happens? You cannot use a glass. So you'll have to obviously go for plastic, right? So whereas if you take a capacitive touch screens, in capacitive touch screens, the concept is pretty simple. You don't need the screen to be flexible. It can be rigid because you're going to use capacitors. It's completely based on capacitor. When you keep your finger, based on the capacitive activity between the finger end and the already available electrical region or sheet, capacitive activity will be produced, and as a result signal will produce, and that will be captured as a touch, right? And in touch, I mean in a capacitive touch, you can use more than one finger, right? Another advantage is we can use glass, right? Now that the technology is like very much developed, we have Corning Gorilla Glass 1, 2, 3. Now they have introduced Corning Glass 6. Samsung's new phone has released Corning glass, Victor's, everything has changed. Now we don't use resistive anymore, right? Okay, so this is to help you understand sensitivity. The reason is like in a resistive touch, the sensitivity will be low compared to the sensitivity that you get in a capacitive touch. That you could have, I mean, you would have experienced. Like yes, you see that in old ATM machines, you can see this resistive touch screen. Right? You cannot, like, the sensitivity there will be very low because of the nature of the touch screen. Right? So we'll move to the next one, threshold. So threshold here means the minimum value required to start an instrument. Okay, so threshold is a minimum value required to start an instrument. For example, if you have a television set, let's take there is a television set which is like 46 centimeter. The screen size is 46 centimeter. Hope you know how the TV screens are measured. It's measured along the diagonals. So let's say we have a 46 machine, 46-inch TV, and to switch it on or to make it operate, we need a particular power, right? If you give a 55 watts power to a 46-inch screen, it will not turn on. It needs minimum 60 watts. That minimum 60 watts is what is called as threshold. So it should reach, I mean, the power supply should go beyond the threshold value to make it operate, right? So in this case, 60 watts is the threshold, and only if you give a value more than 60, 61, 62, 63, then your TV will work, right? So this is threshold, right? So I hope you understood. So these are all the static characteristics of a sensor.